So now what we're going to look at is sort of the next step in the history of security in ciphers. And this was really the generation of the Enigma machine. So this is there's a longer version of the presentation. I'm giving sort of a really quick, trying to keep these 5 to 15 minutes. I'm going to use the slides that are posted. So Ralph Simpson has a version of this that I'm also going to link. That's a longer talk he gave at Google. There might be some other versions out there. But it's really interesting. So it talks a little bit more about the history of the Enigma machine and where it came from, how it was developed, and what it sort of meant for a lot of World War II. So there's a lot of interesting stuff in here. So we looked before at the previous ciphers, and we saw we either had these code books that could be captured, or we had some sort of methods that could be broken fairly easily. So the design of Enigma is part of a series of what we're calling electromechanical rotors. So if you think of sort of older typewriters where they had some motor assists and stuff like this is the next step of this. You basically have a system where you press, the basic idea is if you press one key, it generates a different cipher, right? This would just be like our classic cipher wheels. The thing that gets interesting is that your cipher changes over time. So it's not a constant, A always equals B's. It's changing how it works in various, permutations of your algorithm. So there's some, like most of history, we have this issue that history, especially around military history, gets written by, either something that comes out on top or something is suppressed early on. Enigma is no different. What you actually have is, so there's this sort of idea that the original developer of it was the German Navy, effectively. What was sort of found later is that there was actually a Dutch naval officers invented this idea, this electromechanical rotor that we'll talk about in a second. So the background here is that the Dutch Navy had suppressed the patent at the time. This, of course, changes what's called the original inventor. So if you look at a lot of military history, in fact, this is pretty common. There's quite a few inventions in the security domain that were initially developed in a historical military operation, and they were never publicly displayed or anything like that, of course, for military reasons. And only later it comes out when someone else reinvents them that, actually the military knew about this for 10 years or something like that. So that's going to come up a few other times when we talk about some more modern crypto systems in detail. So we're going to look at specifically modern crypto systems later on. For now, we're just looking at sort of the history of how this all worked. Okay, so this is one of the Enigma machines. So what you have here is you basically have an operation. You have a keypad down at the bottom that you would press. So you could just type your message like a regular typewriter is the nice thing. Up here, and so it's sort of missing a panel that would go here that would show what light is lighting up. So these lights indicate what the output is. So if you hit A, it outputs L, let's say, right? But then the thing is that it's continuously changing. So there's a series of wheels up here that are continuously advancing. And basically these rotors are changing. And as they change, it changes what the cipher is converting an input to an output to. And so this is what it sort of looks like, right? So we have these rotors, these drums actually, remap letters in various ways. So you can see there's sort of some mapping on each one. They rotate, so this changes, as you move through the circuit, which input letter is mapping to which output letter. The complete thing also has this plug board. So there was a number of things that added more permutations to it. The idea is that, you had to have some specific settings that you could tell someone if they use those settings, then the message would decode correctly. If they use different settings, it wouldn't decode correctly. So some of the settings you had was, which rotors were used in which order. You had to set initially where they were set to. And potentially in models that had this plug board, which was sort of a later addition, you also had to set, if there was any plug board changes here. So the changes let you do additional individual letter transposing. So you could change a few of the letters around. And again, it didn't print anything out. It just lit up a panel to indicate what the output message was. So as an example right here, if the A key is pressed, let me just erase my stuff. You can see the rotors are rotating. We have the electricity basically, so you can see the electronic side is quite simple. It's just a circuit that's using these mechanical rotation, right, to generate a circuit that's eventually going to light up a light bulb. And so it passes through all of these rotors, which do the transposing. We have additionally, so you notice there's this reflector at the end. This basically makes it pass through a second time. So we're just increasing how many potential permutations we have and stuff like that. Finally, it could go to another permutation before it lights up a given light bulb here. So in this case, H comes out as the input. So you press A, it lights up with H. And there's quite a number of key spaces, so it's actually, in theory, quite a secure system. So this means that effectively, if you imagine, right, if you wanted to break this, one way to do it is to brute force it. So you could say, well, let's get a message and let's just try every rotor setting, right, and every other, these plug boards and all these settings. So the idea of Keyspace is that it's too big to try that. If you tried that all, it's going to take far too long. So in this case, they give the example, right, if you had 100,000 operators and each one, it takes them about a second to move everything, it's still taking twice the age of the universe to break the code. So that's kind of where the perceived strength of Enigma was. So we'll talk about breaking it in a moment here. But basically, the big problems were, as we'll discover in many crypto systems, it's basically operator procedures. So the operators don't do things correctly. They reuse settings that shouldn't be reused. And in this case, there was actually some particular users that were resending some known data all the time, which is often bad for a security mechanism because it gives you something to look for. It gives you a way to know if you've broken a cipher. It gives you potentially if there is some analysis you can do on it and stuff like that. So they weren't totally, totally secure, even though at first it seems that way. Basically, there was some initial work by the Polish in actually decrypting this. So, like many security systems in the past, that comes down to bribing in some of this initial stuff to get the Enigma keys, right? So they're able to bribe them to figure out what the key is, right? What all these settings are and stuff like that. So you needed the settings. You also needed an actual Enigma machine, right? So some of these you could buy in the open market. Sometimes they were captured and stuff like that. So that was sort of some of the initial work here. The more famous one, so what you might be familiar with because there's a movie about it, was the British effort in breaking the code. And so the British obviously put a huge amount of effort in this. They basically built what they called a bomb. This was actually a mechanical, so if you the movie's pretty good, recommend it, not part of the class, but you can check it out. But you can't look up photos of these. And what this did is it helped this issue, right? So this operator manually checking stuff is crazy. But what if you could make, what these systems look like, you've reverse engineered them. What if you could make something that really quickly can check a whole lot of settings, right? So it's designed to actually check all of these settings. So the idea of the bomb was basically to figure out a way to speed up this such that we could actually have some hope of brute forcing this in reasonable time. And this was helped, even though the key space was large, this was helped by certain restrictions on what many of the settings were actually used as, so that not everything was random, basically. Here's an example of one. So this is this is the U.S. bomb. So U.S. Polish and UK all had versions of this. But these were actually like mechanically sort of wheels that were moving and stuff like that as part of the systems. So this was some of the really early beginning of computing. So it's interesting because this is, again, military gives a lot of push to finish stuff, to do certain things. This was a really good example of that. I mentioned before the capture of that specific U-boat, right? So U-boats, the German submarines, were obviously a huge issue here. So this is one of the things they were really trying to decode, was actually the messages used to transmit stuff to the U-boat. So they could understand what the actual position of these boats were. You could break the code. I don't know where that came from. If you could break that code, then you could actually figure out that. So as I mentioned, U-110 in the previous presentation was one of these captured U-boats. So this was the first one where they actually did get the Enigma machine. So I mentioned before, they grabbed the code books, which helped with some of the ciphers. The Enigma machine was also instrumental in being able to break them for decoding all of the naval Enigma messages. So basically what happened though is that so you see this big lull here, so there's this drop in losses. So this is Allied shipping losses. So if they break the codes and they're able to prevent most of the German U-boats from attacking them, you see these losses drop down. But what happened, so this is going to be very analogous to crypto in modern systems. Well, people evolve. A more secure system came out with this 4-rotor system, right? So then suddenly all their work wasn't able to break it, and there was, additional work involved in breaking those systems. Yeah, so it's pretty interesting. There are a few of these machines around, so you do see them ever so often. So the thing about this is it's actually been kept secret. So let me move myself so you can see. Until 1974, right, in theory. So even though the end of World War II, this was kept secret for quite some time. Now, of course, this is much more widely known. There's a movie about it and everything. And in part, this was because it wasn't clear who else is using these machines. These machines were still, used for some time after World War II even, by other countries and things like that. So you had a lot of value in the break of them and a lot of value in not knowing that they were broken. One of the questions, right, is did they know it was broken? So you had this new system, and there was a question of, was it because they knew that their old system was broken, or was it just luck? So in this case, it actually appears like it was probably mostly just luck, and it was just part of a regular redesign. I say luck, but really they were redesigning for more secure systems. In this case, it was security from other branches of the German military that also had the same system of the naval ones. They wanted a separate Enigma version for the naval codes than was used elsewhere. So it wasn't, in fact, specifically because it was broken, but it also shows that, right, if you are continuously improving the security, this is going to provide some protection against someone who in fact might be breaking your systems and you don't know about it, which is one of the worst security threats possible. So as I said, the original presentation, the longer version that goes into some more detail, I've kind of given you the quick overview of this. You can see it at saferhistory.com. So there's a lot of really cool stuff there. A lot of what I talked about in the previous presentation is also expanded on there. If you're curious about, historical ciphers, definitely check out the website. It's pretty interesting to see where this stuff comes from, and I encourage you to view the full version of this presentation, which I'm also going to link as well. It's a bit longer. It was given at Google, and it goes through all of the details of it. Ralph also has a book, so there's an ebook version of it that has some more photos. It has quite a few photos of the actual Enigma machines too, so If you're curious about them, so for example, here is like those rotors we talked about, so you can see all the mechanical pins. You know, a lot of this stuff is pretty cool, and you can also find clones of the Enigma machine, so people have actually built their own Enigma machine. So if you're curious, if you want to build your own a machine or something like that, that's also something that you could do if you really want. But yeah, so thanks for watching the lecture. Hopefully you learned a little bit about the history of codes in combination with the previous one. And this one, it sort of has brought us up to sort of World War II. So the next thing we'll talk about is what is the point of computer security and computer safety in general. We're not going to talk about new ciphers for a little bit now. We're gonna talk in a future topic about ciphers like AES and RSA and ECC, which are the ones that are used nowadays. So they also have some interesting history to them. But what we're going to delve into now is actually what is computer security and safety, and what's the point of this all.